Today, we're going to primarily be discussing ways that agents can have better coordination between each other. So what I'm showing here is just a little diagram of one of the algorithms we had looked at, an independent learning algorithm. And in this case, each agent is learning its own policy function and learning also from its own reward function, or its own reward values given by the environment. So like it's not getting information about the rewards the other agents are receiving. Of course, in an environment, the reward structure should be set up so that the reward you give to a particular agent is, relevant to that agent's behavior. So, in theory, we only need that piece of information for an agent to maximize its own return. But when you have coordination and behavior of other agents, there are a lot of complications that can interfere with agents actually, coordinating or competing with each other and accomplishing their goal. So here, like the environment has some state which has all of the information available. And here I'm just showing like a cartoon environment where there's two agents in it. And the feature vector that one of these policy networks takes as input could contain all the information in the environment or just some information. It could have information about, for example, where the other agent is, or that could be missing. It all depends on, what the intention is of the problem. But the policy network is going to be trained to maximize this agent's individual performance, conditioned on this input of the feature vector. And then, this feature vector goes into the network. It doesn't have to be like an MLP, like a neural network architecture like this. But if it was, we have these, hidden layers. And then at the output, we have action preferences. This is just an example. Let's say there's 3 actions. So the network is going to output, these 3 values. And then we're going to apply a softmax to turn this into a probability distribution. And then that will be used as the policy function where we'll sample actions from this distribution. So during training, all the agents that this network is trained to, optimize the performance. And then when this is deployed, the agent in the environment, this state will be transformed somehow into the feature vector, removing any information that the agent doesn't have access to. And then this will output, something that we can sample from, and then the agent will take actions according to this. So this is what we had already discussed, just the normal, independent version of the actor-critic algorithm. And here, I'm not showing all the details of how it's trained. This is just like when it's deployed, what do we actually have? So far, is this clear to everyone? Any questions about this, what we're doing with the environment and the action selection? So now we're going to talk about one of the ideas in the chapter about how we can share more information between agents, possibly get better coordination between agents. And this is something called, training policy representations, or, policy representation training. So there is a cartoon of it in the book here. And this, hides some of the details, but what I'm showing here is just a more like fleshed out version of that cartoon. And also we can compare it to what I already had for the independent actor-critic algorithm. So the idea here is that we have the same feature vector, which we had derived for, this feature vector belongs to this particular agent, like the one that we're training. So now this agent, like the one agent which is learning independently in the problem, is now going to train an encoder-decoder network, not to optimize its own performance, but rather to try to predict the policy functions of the other agents. So here, let's say that there are 2 other agents in this environment, and that the agent we're training can see what actions those other agents took. Like in order for this to work, the information about which actions were taken by the fellow agents when there was this particular feature vector input has to be available, because those action choices are going to be used to train this entire network to try to predict what these distributions are, or what the behavior is of the other agents. So really, you can like create a network like this, and it happens to be an encoder decoder network because of how we're using it. But practically, like that, when we train the network, we just have to instantiate some kind of neural network with an architecture where there's some layer in it. Like here, I'm showing it in the middle, where eventually we're going to want to pull out the values in this layer and use them as a summary of the information about how the other agents are behaving. So like on the decoder side of this, we actually need, multiple decoder networks. So like our one agent, it has to predict the behavior of all of the other agents in the problem. So we can set up the encoder network and have this, go to this layer. And then we can feed this encoding into one or more decoder networks in order to predict the action preferences of all of the other agents in the problem. So if there's two of them here, we need like two different decoder networks. You could also set it up so this outputs all of the action preferences like concatenated of all the other agents, but that's a little weirder to train because normally we're going to train this by minimizing the cross entropy loss, just like we would with supervised learning. So it's like we're building a data set of what actions the other agents are selecting, using that as a data set then to train this network. And so during training, this output is not actually directly used. It's only used like for backpropagation because we have to actually ensure that this network is learning what we want it to learn, which is how to most, effectively predict the behavior of the other agents. And even though like we are predicting the behavior of the other agents, now those other agents are making decisions based on their own feature vector input, right? Now the agent that we're training here doesn't have access to that, right? It can only see its own feature vector. So this whole encoder decoder network can only be conditioned on its own feature vector, which may mean that it can't actually, like there's a limit to how accurately it can predict the behavior of the other agents, right? But we're stuck with that limitation anyway. And the question is, how much can be learned about how to predict the other agents, even though we don't actually have access to all of the information those agents are using for their own policy functions. So does this make sense to everyone? Any questions about the architecture of this or the goal of setting this up? So we're going to train this, right? Like this whole other decoder end of it is relevant for the training process. But we only actually need it indirectly. When it comes to actually using this, we're not going to worry about the decoder network, because the entire purpose of doing this is so that we can take, our agent's feature vector, and normally in vanilla, actor critic, this would then be used as input to the policy network, right? And that would be used to output actions. But what we're going to do now is we're going to feed this feature vector into the encoder network. Then we're going to get from the encoder network, it's going to output this representation, right? Like we're going to pull out of it this layer that we've designated as like, this is the layer we want to use to summarize information. And we could also like here I've drawn it where this layer is smaller than the hidden layers. It doesn't have to be smaller. This is just a way of sort of forcing the information to be compressed. often, like when you set this up, you want to make sure that this layer doesn't have an activation function applied to it, which is going to squash it or cut it off somehow. Like we want this to be to just have like a full range of values, just be like an untransformed output. So we're going to get the output from the encoder network and then concatenate it with the feature vector itself. So now the policy network is going to take as input the feature vector it would have used originally, plus the policy encoding layer, which is the goal is for this to summarize everything it can learn about the behavior of the other agents. And then its policy network is just the same. It's just the policy function that outputs its own probability distribution over actions. But now it is conditioned on both its feature vector and the policy encoding it's learned during training. So in order to deploy this now, we need both the encoder network and the policy network. And to use it, like we have to send the feature vector through both of these now in order to get an output from this. So does that make sense so far? Okay. So here, I just have a few bullet points on how this type of training is supposed to work. So because we're just learning these representations, any sort of algorithm where we can observe the actions of the other agents, we could add this to it potentially, where we're just learning this representation. And what we would do is whatever function we're learning, like here I've shown an example where we have like a policy network, but if we were doing value function learning instead, we could condition the value function, on this these learned encodings. Now, it's possible that there are cases in environments where maybe we can't observe the actions of the other agents. Like maybe they're hidden from us at certain times if an agent is too far away. And in that case, this is not essential to the training process. We could just fix the encoder decoder network we have at the time. And if we had a step where we didn't have access to that information, then we just would skip the gradient updates there. I mean, we'd still have the network trained on whatever it's learned so far, right? But we don't necessarily like the other parts, like information we need on every step. This is something where we could skip, certain training steps. So the goal for the encoder is to summarize the information about the other agents. When we do independent learning normally, whether it's value or policy based, the actions of the other agents influence the returns our agent gets in training, but it's an indirect process, right? Here we're trying to directly take information about the actions of the other agents and incorporate it into the training process. Now, it's not used when we deploy these agents, right? That information has to be captured in the encoder, but right, like the encoder itself is not predicting the actions. Like that's the decoder network is doing that. So we're not directly using the predicted actions. What we're doing is just using some abstract vector that hopefully summarizes, that information, something that's suitable for our policy function to condition itself on. But, once we deploy the agents, it's the same as we had before. We just ultimately have a function of the feature vector, right? We don't have a function of anything else. Like if we look back at this, yes, we do have to pass it through the encoder network, but this encoder network's already been trained. We have the policy network, and this entire combined train network is still just a function of the feature vector. So it doesn't really change much at deployment. We just have a little bit more of a convoluted architecture, but right, this is still just a single output function of the feature vector that we have. So now that we've gone over how this works, we can look at some examples of how it, maybe some more practical things of how it works in coding, and what it looks like. But are any questions about how this whole thing works and what the goal of it is? Again, here in the book, this is the diagram we have, where here we have here that they've written it out as this like observation for an agent. This is going to be mapped to some feature vector for the input, but how this then goes as input to the policy function, and then we pull out this representation also as input to the policy function, right? But it's still just a function of this. So now the book, obviously, it doesn't like have a full like pseudocode example of this. I'll show some of the implementation I have for doing this. But going back to this test environment we've been looking at, there have been a lot of graphs in the book of this environment, and they're all kind of inconsistent because they're different variations of it. Like we've seen other versions of this where, like here, the ideal performance would be 1. So here, actually, neither one of these curves are reaching ideal performance. But the claim here is that if we add this agent modeling or policy representation, that we can get a higher performance and more consistent performance across training runs. Because here we also have lower variance. Now, this entirely depends on how you train it. So I'm going to show, using the same example throughout of this environment, different learning curves for this using agent modeling and not. And we can see, what kind of advantages we end up getting from using it. But the claim here is that with this environment, we should get, actually, I guess like the training here isn't necessarily faster, but that the end result is a more optimal performance. And here, the environment is one set up where the agents all have to cooperate on every example. So the idea being like, if they have to coordinate for every item collection, it's a harder task. It's one that would be better suited for this policy representation to help, because the idea is that with these representations, the agents can better learn how to coordinate together. Because, right, they don't just have to guess about what the other agents are doing. They can actually, predict that information directly. Okay, so let's look at some of the implementation stuff for this. So in order to do this, right, you need a way of like combining these inputs. So like here, if I take like the code for the original like actor critic method, we're usually taking these feature inputs, and we're also doing this in parallel. So we have like parallel environments. We're creating this feature input. And here we need a way of, getting the encodings as well, and then concatenating these together. So this is just a way where these are being populated together. And these are just like different functions that combine these feature vectors together into this combined input, which is going to be used to actually do the action prediction. These are just forward pass functions for the neural network. If we look at like the actor critic code for this, all the code, like the nice thing about it is it looks almost exactly the same as the independent actor critic algorithm. It's just that we have now like another set of inputs to keep track of. We have the encoding vectors we have to generate, and then also the combined vectors that are going to be used, where we're concatenating feature vector with the encoding vector. But otherwise, everything's the same. And also, every time we do a prediction, like here, this is getting the joint action selection, where we sample the actions. And in order to do that, first we have to update, all the encodings, right? Because all these agents now, they're going to be unable of making an action prediction unless they also have that encoding output from the encoding network. And then eventually we have our, let's see, the back propagation step I have here too. So here, like, I'm using the psi symbol for the gradient of the encoder decoder network here. But here, like the way I showed it before was that there's like a single encoding network for one agent, and then there's this family of decoders. So that's why, like, here what we're doing, this is doing back propagation using the actions now of the other agents, where now it's minimizing the cross entropy loss this on with the feature vector input. Right? And this is also going to extract the encoding vectors out of the middle part of the network. But here, like the encoder decoder network, even though there's just going to be like one set of encoder params for this agent, but then this is doing backprop separately for every other agent, because this decoder network, right, it has to predict the actions of just a particular other agent, and we repeat that for all of the other agents in the problem. And then the way I, let's see, wrote this here. So we can look, let's go back to this level-based foraging problem we had looked at before. So does anyone, this is the problem also shown here in the book. Does anyone need a refresh of how this problem works or what? It's the example we've been using throughout almost the entire textbook, basically. So if everyone feels comfortable, but if anyone doesn't remember or wasn't here for a previous meeting where we went over it, I can, explain how it works. Okay, so I have this version of the problem. I'm calling it here, let's see, this variation of it, LBF just means level-based foraging. So here I'm labeling it 2288. I just started naming it like this, so it's a little easier to distinguish the different environments. But this just means when this environment is initialized, there's two agents, two items, and then this is an 8x8 grid. You can see that's what's shown here. And this is not a case where all of the items require cooperation. This is going to have a mixture. So some of the items could be collectible by a single agent. Some of them will need coordination between the two agents. And by the way, another comment on the performance of this, there is always, different ways to construct the feature vectors for this. Now, here I'm showing primarily like a relatively encoded feature vector where there's positions of everything, of the different agents and items. Now, you could encode this information so that you have the absolute position of everything you provide to the agents. And then they're going to have to figure out, their relative position. In this version of it, the agents, like here, you see how we have this for this X and Y coordinates? I'm computing the X and Y distance between other relevant things in the problem. So now the feature vector is from the perspective of this particular agent, where all of this position information, this is encoding position information about the other agents and also of the items that are in the grid world. This is encoded as relative information. And I'm also, because it's a discrete grid, this is all one hot encoded. So I'm like creating, it's not exactly one hot encoded because I'm actually using negative numbers too. So I have a convention where if an item is to the left or below in the Y direction, then it will be however many units away that is in the encoding, from, 1 to X or to X minus 1, because there's like the actual agent position. It can't be more than a distance X minus 1 away from anything. And then it'll either be a positive 1 or negative 1, depending on what side of this. So it makes the encoding a little more space efficient. And then there are there's an additional piece of information for all the other agents and items, which is their level in the problem. And here I create a normalized level. So these are all values between 0 and 1, or 1 is like the maximum possible level. But now it's encoding this information as just a single value. So it's like for any other agent out there or any other item out there, this is the relative level that thing is. And there's if the agent has a higher level than anything, then this value is just going to be 0. But I also made a different version of this. As I was training this, I thought, well, the level information, these are also discrete levels, right? Like there's some maximum level here. I think there's a value of 4, the maximum level of any one agent or item. But, this level information really might be better encoded also as like a one-hot encoding, so that we have this like discrete information at the level instead of it needing to be this real number that somehow has to be compared. And then our neural network is going to have to learn like greater than or less than functions, within itself, which might be difficult. So here, this version of the feature vector encoding does the level encoding also as just like a sort of pseudo one-hot vector. I'm also using a convention of -1 and 1 if the agent is a higher level than the other item, or a lower level. But it's the same idea as the position encoding, where it's going to, sort of mark in the vector a 1 or -1 in the position that indicates how far away either that the x coordinate is or how far away the level is. So we can see what impact this has on training. So here I'm training now these different, for now that this is all like the independent actor-critic method still. So for simplicity, we're just talking about policy training here. And it's that same 2288 environment. And so here's a learning curve for just the normal actor-critic algorithm with, and here's like the neural network architecture. So there's just like, there's 2 hidden layers of 64, size 64 each. But go down and compare these learning curves. So actually ignore this one for now. So here we have 2 different learning curves, kind of like what we have in the book, where here we have the vanilla actor critic, and this is showing the number of training steps. And then this is the algorithm that uses the representation learning. We can see in this example, not only did this learn faster, right? Its performance is greater at every point in the training, but it also reaches a much higher level of performance, right? This is like the average reward per step. If you take the inverse of this, it tells you roughly like how many steps on average it takes to collect all the items. And I think I have actually, okay, there aren't, so this is how the training went with that, the first like relative feature vector. So remember what these numbers are. So this is like the higher, the more, performant it is. Here, this is showing also the reward summed over the 2 agents. So like I'm taking all the reward. This is a mostly cooperative problem, so we can use this as a proxy for performance. We can see a little later that actually this environment is not completely cooperative. Like there are cases where agents might compete with each other over rewards. So these type of learning curves are not always the best way to assess performance in this environment. If we look at these learning curves, actually show the rewards for both agents throughout training. And we can see that we don't have to worry too much because they appear to be tracking very closely. So, if they were like oscillating a lot up and down between each other, then the summed learning curve might not be useful at all. But in this case, we could see that it is a pretty good proxy for the overall performance of both agents. Now, if we look at the second feature vector, the one that encodes the level information, right, in a more sparse manner than just turning it into a normalized number, now we can see, Yeah, wait, this, okay, this is the representation learning point. 0.5. So the vanilla actor critic algorithm does a little better with this. Actually, so if we look at actual, let me see also, is this also fewer training steps? So this capped out, its performance maxed out after about like 12 million training steps. And here this is taken longer, although like the performance is a little bit higher. But yeah, for the vanilla actor critic. So actually, we're going to look at another variation of training involving parameter sharing later, where this other feature vector has an even bigger, um, a bigger advantage. But you can always compare training between different ways of representing the state information. And here, like I would just guess from the way it's structured that this method would work better, or at least maybe train faster, because there's a more straightforward route to comparing the level information with that type of encoding. But you know, at the end of this, there's this other method here. Yeah. So for now, ignore this diagram to the right. Okay. So we can just look at these two. So this is showing an episode actually playing out in this environment. Yeah, between the vanilla actor critic algorithm and then the one that uses policy representations. So I have a few different like episodes I've sort of curated here that we can look at. But first of all, we can just see, how it plays out by step. So I'm showing here like how many steps it took to complete. So this is 9 steps, and this is 10 steps, right? The one that doesn't use representation and the one that does. And we can also see the returns for each agent and the sum. So notice that this version that uses policy representations, right? It actually takes more steps here to complete an episode. But we could see the returns are more evenly shared between the two agents, and the overall, sum of the result is slightly higher. Now, this algorithm is not directly optimizing the sum of rewards because, right, this isn't like a common reward problem. The agents get distinct rewards based on which items they individually collect and how they participate in collecting items together. So it's not this number, we shouldn't necessarily expect this number to be higher or lower for one algorithm, but we can see sort of how the agents are working together to do this. Like here, these two agents have exactly the same reward in the problem. Whereas for this one of the agents has a much higher reward because either it collected an item on its own, or it was able to share in the collection of an item that otherwise, could have just been collected individually. So we can see if I advance this forward. Why is this not working? Uh, hmm. Okay, sorry. I don't know why this is not actually updating. Okay, well, if this isn't gonna work, we might have to move on to something else. I can show it maybe next time. But let's see. I did at least write down what happened in these episodes. Yeah, so I believe what happens here is, yeah, in the in the vanilla actor critic policy. So you can see here how this agent is level 2 and this agent, or sorry, this both agents are level 1, right? So this item can be collected by one agent, and this item needs both of them to work together. So what happens in this algorithm is that this agent, which is close to this item, just goes over to this item and collects it. And then this agent is here waiting. And then, it has to wait to collect this. Now, in this case, what happens is both agents, even though it takes an extra step, go up to collect this item first. And then they both go together to collect the second item, even though only one of them is needed, but they still end up collecting it together. So it shows, I guess for this agent to go up here, it needs to have the confidence that this other agent is also going to follow suit, as opposed to, going down and stealing this item from it, which it does appear to learn from that. So it just creates a different policy, right? Like, it's, even though the actual learning curve performance is not that different, it does end up creating a different type of coordination, where in this case it results in both agents having exactly the same reward, because they both end up sharing collecting the two items at the same time. Whereas this version of it does the slightly more obvious thing, which is, since this agent is very close to this item, I might as well just go collect it, even though, without thinking about the impact it might have, where they could both potentially get a higher reward if they skip a step, delay, this takes one step longer, but they can both collect this item 2 up here. There's this. Yeah, this is a case where with coordination, this just happens, this collection just happens faster overall, results in a higher reward than this one here. But yeah, this isn't as straightforward of an example of the behavior being different, because we can see the reward split between the two agents is very similar. But this just happens faster. There's just better coordination at navigating the direction, actually getting up to this item. This other, let me check if, hold on. Check here. Just gonna cancel this, and I have another environment to look at where I hope the oh my god, is this not working? Hold on. Okay. This one is working. Okay, so here, well, we can move on to this other environment for now. But yeah, the point is, we can look at learning curves like they show in the book. We can see, okay, this has better performance. Of course, this is sort of making it seem like this is a common reward task where there's only one reward value we care about. The reality is, it is a little more nuanced than that, where, right, we have potential conflict over certain item collection, right? And that's driven by the fact, in this case, it's not that obvious what should happen, for an individual agent. And also, yeah, if we are just trying to maximize this sum, there is an obvious thing that we should do to do that. We could see, it involves, one agent getting a better reward and another getting a lower reward. So if we just train them this without sharing any information, we don't know exactly what's going to happen with how the agents are going to coordinate. If one has an opportunity to get a higher reward, it may end up doing that, even though it ends up sacrificing the reward for the other agent and also the reward, between the two of them. So yeah, this parameter, policy representation thing, you can apply it to any algorithm, any environment. What it does to the actual performance of the agents is going to depend on what type of environment it is and how much, competition there is. But in theory, the idea is, this learning curve is at least some evidence that in tasks where there is a lot of coordination required, it has a better chance of learning, how to accomplish that. So that is, one piece of how agents can coordinate better together. The other concept we're going to talk about is this concept of homogeneous agents. And now this is a case where even though we have these distinct agents in a problem, they may or may not be interchangeable. And there's a couple different definitions here of what this looks like. I also have, here, I wrote out some notes about this. So with this U, right, this is the convention in the book for writing down the return function for a particular agent. So this is like, what is the discounted return a particular agent would expect to get following its, when this joint policy is being followed. And this joint policy is the collection of all of the different policies in the problem. So if this was like U1 of pi, it would mean what is the return that agent 1 expects when all three agents are following this policy pi 1, pi 2, pi 3. Now, let's imagine that we just permute this joint policy so that now what once was called agent 2 is now going to follow the policy of agent 3 and vice versa for agent 3. Now, if the agents, there's this condition of weakly homogeneous agents. And the idea is that if the agents are weakly homogeneous, it means that if we consider, the same agent, like in this case, agent I, or like agent 1 wasn't permuted, that the performance of the agent, like keeping track of the same agent policy through the permutation, is not going to be affected by this. Okay, so we could swap around and just like relabel what policies the agents are following, and it wouldn't affect the expected performance or like the overall average outcome of a game. It might affect the outcome of one particular game if we change the performance, but this is not the performance from one particular game, right? This is an expected value over all the different iterations that a game could take. So this type of homogeneity is relevant if we have an environment where the initial properties of agents are randomized. So in the level-based foraging environment, the agents are instantiated in the grid in random locations, and they have random levels. So if we swap, like if we have two particular policies that we have that we're tracking the performance of, and they are distinct policies, but if we permute them or interchange them and then look at the performance over many different episodes, it's not going to affect the outcome, right? Because we don't know ahead of time, like those policies are basically getting assigned to random agents anyway, right? Like it's not like we could take the policy for agent 1, sometimes it's going to be in one location, sometimes it's going to start in another location. So in the course of a single episode, they have a distinct identity, but over the course, of multiple episodes for an entire task, they are interchangeable without affecting that. So it's really, the definition looks kind of a little confusing, but really the way to think about it is if we have an environment where, like, if we try to identify an agent somehow, whatever we thought was making that agent, identifiable, like if we had an environment where one agent started in the upper left corner and the other started in the lower right corner, then it would not have this property. Because if we interchanged it, then we'd expect the behavior to be different if those agents are behaving differently. But if we had an environment where they just swap locations randomly every time, then basically both, like the policy is going to end up in one location or another randomly. And, whichever one, like it's not going to actually affect the overall outcome. Does that definition make sense to people? Weak homogeneity?
It seems like, the difference between a weak and strong homogeneity of the policy would be that for week one, that swapping out the policies between each other with any order does not change the distribution of it. Essentially, while strong homogeneity, it seems like the policies are exactly the same.
Yeah, so strong. So obviously, like we could always, create a joint policy where all of the policies were the same. Like regardless of what type of problem it is, like we can always make identical agents. However, if we do that, that doesn't mean the environment meets the criteria of strong homogeneity, which I haven't explained yet. But with strong homogeneity, we have to have weak homogeneity, which means that everything's interchangeable. The agents, like there has to be some, right? If the agents spawn in locations, there has to be some randomizer for the location so that whatever agent we identify, it could basically be interchanged with any other agent. But the other criteria for strong homogeneity is that there is an optimal joint policy, right? This pi star, and that the optimal joint policy is one in which all of the agent's individual policies are identical functions, right? And this is of course identical with respect to their input, right? So like we could still have the input, like the feature vectors, be distinct for each agent. Like if we have relative feature vectors where those agents are being shown what position they're in relative to everything else, that would be fine. Like the agent, like the policy function is then going to react to where it is relative to other things, but that reaction could be identical, even though, right, the input is going to change. It's sort of an important nuance that this property wouldn't, if you had strong homogeneity and that was true with the relative positions, if you tried to make a feature vector that had absolute positions, then of course this isn't going to work because you can't have identical functions because the functions have to be different. Like if you're just saying this is the position of agent 1, 2, 3, 4, 5, now you've fixed the position information of agents, of particular agents, right? They're not going to be randomized or relative. So then the policy function has to know, okay, I'm agent 1. I need to distinguish what the information of the position of myself versus the other agents. But that's why sometimes it can be very helpful to have these relative feature vectors. So that way, like you're more likely to be able to have homogeneous agents because the function itself doesn't have to figure out that relative information, right? You've already baked it in to the feature vector. But also, there's this concept here of an optimal joint policy. Now, what is that? When we talk about ordinary reinforcement learning, the optimal joint policy is something we talk about all the time. It's the one that achieves the highest possible discounted reward for an agent. But in multi-agent learning, we usually don't talk about the optimal joint policy because often it doesn't exist. It doesn't mean anything. Because in multi-agent learning, there are different rewards for every agent. Now, there could be an equilibrium solution. An equilibrium solution would mean that the agents cannot improve their reward by changing their behavior. So that's like a Nash equilibrium solution. And we may find that. I mean, it turns out that is not only hard to calculate, it could even be hard to verify. Whereas, so what does this mean now? Like, what does this imply then? If we're saying we have strong homogeneity, it means that we're putting a further restriction on the multi-agent problem, like in order to even claim that we have an optimal policy, right? Do people see that? Like, or does anyone have an idea of like what that restriction is or has to be to even, like guarantee that there is something that even exists that we could call the optimal policy?
Well, wasn't there, the thing about, optimal policy that, given that some of the previous, chapters noted about different equilibriums, which, can exist in like the zero-sum games, or usually, but then they might
Well,
have
zero-sum
different
game, we
conditions.
have minimax solution, right, which is, again, like that's an equilibrium solution. Um, yeah. So we had previously equilibrium solutions that occur in all different types of games, whether they're, minimax equilibria or Nash equilibrium. But those, right, wouldn't be necessarily called optimal solutions in the same way. Like it's not really globally optimal, right? In fact, in a minimax solution, you have like a stalemate between two agents. So it's optimal if you're facing an optimal opponent, but it's just like it's not the same terminology that we would use, like when we talk about optimality in single agent reinforcement learning, where there's like a very clear meaning and it's unambiguous and it's also unique. Like there's a unique optimal value that an agent can achieve in any reinforcement learning problem. Whereas here now that's no longer the case in multi-agent learning.
And then I recall that there was something about, in previous chapters that was noted that, if any changes of any one of the agents, causes further changes in behavior of other agents, it might, be, one criterion for optimality, because it means that no agent can do anything meaningful in order to improve the policy or something like that.
Sure, yeah, that's you like the equilibrium criteria, where every agent is sort of stuck, where they cannot improve their own reward by changing their behavior. That would be a property of any equilibrium solution. I mean, we talked about Pareto optimality before, which is an equilibrium solution that also has additional properties that, because it's a way of distinguishing between different equilibrium solutions. So here, what I've written at the bottom here is that, there is a type of game. We haven't really looked at much of them yet, because level-based foraging is not an example of this. But if we have a common reward game, that means that the rewards for the agents are identical. So whenever one agent gets a reward, it's the same value is given to every agent. And that effectively does make the multi-agent problem a single agent problem. Like it makes it map very nicely onto a single agent RL problem. And then we do have an optimal solution, just like we have with single agent RL. And they talk about this homogeneous agent thing with the next environment we're going to talk about, which is a common reward environment. Yeah, so it doesn't mean that you can't have strong homogeneity be successful in an environment that isn't a common reward environment. It's certainly possible, but it's not exactly guaranteed in the same way. And it depends on how the solutions work. I'm going to show you can apply this concept and try to make it work with the level-based foraging game as well. And it can have success. It's just that it may just be working because it's mostly a cooperative game with common rewards, but you get situations where there is no unambiguous optimal solution. You just have different solutions that have different properties depending on what you're prioritizing in the problem. If you're prioritizing coordination and sharing rewards between agents, or if you want like we could always turn level-based foraging into a common reward game explicitly, but the way it's set up now, it's not. Like if one agent collects an item and the other doesn't, then that one agent gets a reward exclusively and the other agent does not. So let's talk about a game, a new environment. So this is called a landmark game or landmark environment. The idea is that we have some number of agents. Here I'm showing 3. And then there is some number of landmarks, the same number. And the agents and landmarks start out in random positions. So we have that, randomization property. And the goal is for all of the agents to move to cover the landmark, or to move into the same grid location as where the landmark is. And then once all of the agents are simultaneously covering a different landmark, right? They have to all cover a different landmark because there's an equal number of landmarks to agents. Then they all get a reward of 1, and the episode is over. So the agents just have to disperse themselves and cover the landmarks. And in the first version we're going to look at of this game, each agent can see the position of the landmarks. Let's just say, for simplicity, it can see the relative position of itself to the other landmarks. But it cannot see the position of the other agents in the problem. Okay? It can only see its own position relative to the landmarks. So the question is now, we have this game set up with this type of input, right? Like, actually, this condition of the homogeneity depends on the information available to the agents as well. So given how I've set it up, is this, an environment with homogeneous agents, and is it weakly homogeneous or strongly homogeneous?
Well, I don't think it could be a strongly homogeneous, because wouldn't that require basically having the same end state in order for that policy to work properly?
Yeah, so if it's strongly homogeneous, all of the agents would behave identically with respect to their own input. And then the question is, if they do that, is this task going to be possible? Like, again, there's a chance. It's an interesting question of how, we'll actually see how this would work if we try to impose that constraint. But yes, it seems like, but again, like, why is it not, why can their behavior not be identical? Again, it's not that their behavior is identical, right? It's identical, the function is identical. So it's going to be identical with respect to the input, right? It could still behave differently if the input is different. But there's a reason here why identical policies will not work the way this environment has been set up. So does anyone, if no one has an idea of why, I can talk about it and then move on to a follow-up question.
I don't have much of an idea that, other than that, in the chapter segment was noted that if that limitation about how homogeneously strong would basically make them go into the same goal state, but that doesn't work because the goal states are different.
You mean like the same landmark?
Yeah, the same landmark.
Yeah, so let's say, like, so first of all, I've labeled these landmarks with different shapes, but in reality, the landmarks are also unlabeled. Like, they're just their position is known, but there's no identifying feature of a landmark. So we just know a landmark is there. This problem would actually be easier if the landmarks had a distinct, label on them. Because if that was true, we'd still have this problem, but right, like, let's say agent 1 was like, well, I'm always going to go to this landmark, right? If they set up this idea where they go to different landmarks, that would be possible if the landmarks were labeled. That wouldn't be strongly homogeneous, though, right? Because they have to have distinct behavior. Now, the reality is they're going to have to decide what landmark to go to based on just the position information. So, you could imagine these agents say, well, like, what if the agents just go to the closest landmark to them, right? Like that would be like strongly homogeneous agents could do that. They could have that policy where they say, okay, we're just going to look at the grid, and whichever landmark is closest to me, I'm going to go there. However, that's going to have problems, right? Like could you see why that is not going to work reliably?
Well, in any grid, there could be, basically an equidistant, between two landmarks, and then, two agents could possibly, choose to go to the same landmark
Yeah.
if the
Or you
distance
could just
is
have,
short.
I mean, you could also have two agents that are just both closest to one of the landmarks. They're not necessarily equidistant, but they're, farther away. So, okay,
Yeah,
we could,
or that basically all three agents are basically close to one landmark and the other two get ignored.
yeah. So now let's say we don't, the agents are now weakly homogeneous, meaning that they're interchangeable. Now, right, if we have a weakly homogeneous problem, we can just train it like the way we normally would. We don't have to think about it, right? Like the fact, it's just that during the training process, the agents might develop distinct behavior. And this problem, it seems like they probably need to. But, you know, if they're going to develop distinct behavior, the agents have to, each agent has to develop some sort of heuristic that works between them where, let's say agent one is like, I'm always going to go to the landmark closest, to this corner. Like there has to be some way of deciding based on where the landmarks are, a particular agent is going to reliably go to just one of them, and it's going to be distinct from the landmark the other agents go to. So if they learn how to do this task reliably, then the agents are going to clearly have to have, distinct behavior and follow some kind of convention. But, we can see an example of how they actually coordinate. But there is this follow-up question, which is, let's say that the agents could see the positions of the other agents. Okay. So here I've said they can't see, they can only see the position of the landmarks. Let's say that each agent can see everything, can see the position of the landmarks and the position of the fellow agents. Does that then change whether the problem has the property of strongly homogeneous agents or weakly homogeneous agents?
Well, if they can see each other, then couldn't they basically determine who's nearest to each of those landmarks and basically
Yeah. So like I'm gonna contend that if the agents can see each other, then you could solve this problem with strongly homogeneous agents. Their behavior could all be identical with respect to the input, because you can have a single input function that learns how to separate the agents. They can move away from the other agents and towards a given landmark, and they can learn how to do that. Now, if we have strongly homogeneous agents like this, we can take any of the algorithms we've already looked at, and we can actually make all of the parameters equal to each other. So like we can still keep the algorithm the same, where there's a training loop and we go through, each agent is trained and its parameters are updated. But we can just like point to the same set of parameters for every agent. So then every time we do a training update, you're going to be updating the same set of parameters. So it's much more sample efficient because the same set of parameters are going to be getting updated from every single experience example from every agent. So hopefully this would learn a lot faster, but it's only going to work if the environment has this criteria, which is it's possible this will only work well in a common reward game or a game that is very close to a common reward game where it's a mostly, cooperative situation between the agents. Okay, let's actually look at the performance of this landmark game and see what it looks like. So, this is a version. the game where it's the original version. We're now, so the agents are going to be blind to the other agents. And this is showing just a vanilla training run. I'm just going to skip down to the actual learning curves here. So here's an example of training this with all the different algorithms we've talked about. So we have vanilla actor critic. It takes a while or doesn't learn anything, and then suddenly it figures out how to do this. Then this is with policy representation, right, where we have the encoding. Now, this is okay, right? This is a game, this we said is like a weakly homogeneous agent game. Doesn't really matter, but this is clearly a case where coordination really matters. Like the agents have to very quickly develop a distinct identity based on the other agents. And it seems like in this problem, the policy representation learning really works well. Like it causes the learning to occur much faster, and it even has a higher end performance. I mean, it's about the same like end performance as this, but maybe even slightly better. But the important thing is it just learns much faster. Now, you can also try to train this as if it's strongly homogeneous, right? If we do parameter sharing, this means that I'm just setting the parameters of the policy function to be shared across all the agents, right? So this will only work, and we can see that this is not working. I mean, it actually learned something, right? The performance is not zero. It is achieving something, but it's clearly nowhere close to optimal because we already said this problem is not a problem that can be solved with strongly homogeneous agents. We can see also this is the performance of this. So on average, it takes 8 steps for both of these basically to work. Or like the median is 8 steps. And the homogeneous agents have a median of 35 steps. Really, actually not horrible. I guess it's kind of surprising. Let's see. If we do this randomly, so if you do this landmark task with random behavior, the median time to finish is about 300,000, or no, 30,000 steps. So the strongly homogeneous agents actually learned to solve this in like 35 steps. Here, which is pretty surprising, I guess. So we can see an example of some episodes. So, right, here's vanilla actor critic. Here's this. So we can see if we run this, the agents are going to disperse and end up covering all the landmarks. And you can see where they end up isn't really based on where they started. Now, I guess what's interesting is what are the homogeneous agents doing? So they sort of tried to split up, but now we see there's 2 agents overlapping here. And the way their policies are set up, there's some degree of randomness. Now, this agent is sort of waiting around and deciding to move to one of the other landmarks in case it's in the way. And eventually, one of these agents is going to split up. And if we make this go long enough, this is going to eventually, I mean, they have some method of dividing themselves, but on average, it takes way more steps because they have to have some stochastic behavior where they sort of sit in one place and then eventually decide to split up and then hope that the times that they split up happen to coordinate. I mean, there's some probability of them waiting at a landmark because they were able to leave, and these things have to happen simultaneously. What we should see here, actually, if we run a different episode here, is that where the agents end up sort of corresponds to their identity somehow. So like agent 1 is in the left, agent 2 is at the top, and agent 3 is at the bottom. We can see if that sort of continues. It's probably going to be a little hard to see exactly what convention they're using. What did I say last time? Was agent 3 at the... Okay, so here we could see like agent 3 starts close to this landmark, right? But whatever convention they've chosen, agent 3 knows, okay, I can't go to this landmark even though I'm closest to it because I am the agent that has learned I have to go to this landmark because I have, a unique identity, and I have to make sure that, because it has no idea that this other agent is far away from this. It could be right here. All it knows is that there is some other agent in the problem that in all likelihood is going to go to this landmark, even though it started closest to it. And here, this actually failed. It didn't. This didn't run for enough steps. I mean, here's an example where the parameter sharing actually solved this in 7 steps, even though, I mean, it just got lucky this time where the agents just kind of happened to, I mean, this actually solved it even faster than this one, right? Because in this case, it just, everything worked out perfectly and they got lucky. These agents, though, right, have to actually go to distinct locations. And agent 3 here is on top. So, right, but it's kind of like how you would coordinate this with other people, or like if you knew you were going to be blind to your fellow teammates, you would have to agree on some method of deciding which landmark you're going to go to in a way where you're always guaranteed to go to separate ones, right? Where here, the only identifying features of the landmarks are where they are in the grid. If they were labeled like 1, 2, 3, it would be trivial, right? You would just tell your partner, you always go to landmark 1, you always go to landmark 2. But here, they actually have to be identified somehow by the agents. We could see this didn't take that long to learn, right? Especially with the parameter representation. This is only like 1.8 million training steps. And also, is this the one with shared? Yeah, shared parameter. I mean, it only took 5,000 seconds. Like, this isn't that much training time here. Actually, I just kept the architecture the same as for level-based foraging. It seems to be plenty powerful to solve this task. But I said that if the agents have access to full information, full position information, so they could see the position of other agents, then it changes the problem, right? We can see here learning curves for this. Now we have a situation where this is now a strongly homogeneous task. Like this, there is an optimal solution here. The optimal solution should be one in which the policy functions are identical because the agents are all interchangeable, and there's enough information in where the other agents are to actually, split up optimally. And we can see here that the vanilla actor critic algorithm does about the same as before. Actually, it seems, even though it could use that information, this seems to be performing the same way. Actually, same with the representation learning, where now, if you look at the actual end performance numbers here, it's the same as before. So the agents basically have a unique identity, even though they don't need one. If we look at the parameter sharing learning curve, now we're actually forcing all the agents. It has to now learn a solution where the agents have identical policies. And this solution, because we know the properties of this game, this is the optimal solution, and we're actually forcing it to learn the optimal solution, which has much higher performance now than these. And now the agents don't have to go to a particular landmark that they've identified based on their identity. They can actually split up optimally. Here we could see the median time is now 6 steps instead of 8. So these two versions learned the same solution as before. But we can now see, so what I'm showing on the right here is the parameter sharing version of the algorithm. And if we look at it and its behavior, we should basically see that the agents go to like what is their closest, possible thing. So here, like agent 3, even though agent 2 is closer to this than agent 3, right? Agent 3 is going to be like the limiting factor here. Actually, maybe 1 or 3. But agent 2 knows it has to go here in order to give space, right, for 1 and 3 to get to their closest landmarks, right? But notice like these other solutions, like who knows if we train this longer, maybe if we train this for like 100 times longer, it would eventually like transform into this solution, and it would learn how to like the strongly homogeneous solution. But that's going to be a little difficult. Like this is already a pretty good solution, right? This is like sort of a local minimum in the policy space. But if we do I mean, I don't even know theoretically if this is guaranteed to find, this solution. But the nice thing about doing parameter sharing is that we force this solution on the problem. And also, you could actually use this to automatically learn, like swarm conventions of how to best position yourself with respect to other agents in the swarm. But here again, it's like 5 steps. These take 7 steps. But yeah, they sort of learn to optimally split up and give room and coordinate in the best possible way. So we have sort of 2 extremes here. One where the agents are identical, they have full information, and they're able to best, coordinate and go to the place that is going to be the best outcome for all of them collectively, right? Because this doesn't end, like it doesn't matter if one agent reaches the landmark. They all have to reach it at the same time. But, on the opposite end of it, we have, right, this solution where even though like this strongly imposing this strong homogeneity on the problem shouldn't work, the identical agents, like here it's like 58 steps, like it still found a way to solve this way faster than random behavior, where they sort of move into position and hope for the best, and then they have they've learned some stochastic behavior that reliably, within a median time of 35 steps, eventually will cover all the landmarks. So you can kind of, regardless of whether the solutions are optimal or not, you can use these different versions of the environment and the algorithm to study like what is the best you could possibly do under constraints that you might actually face in the real world. Like you could have a constraint where you are going to have identical agents, and it seems like it's sort of doomed to work because there's just not enough information to solve the problem. But there is some clever thing they can learn how to do, policy-wise, to figure this out. So I think, yeah, this landmark environment here, they have it in the book, but they didn't actually have any like learning curves or graphs of this. But this landmark environment is very simple, so it's pretty easy to set up. And it's a pretty good way to illustrate the different, versions of homogeneous agents. So again, with want to force homogeneous behavior, we just share all the parameters. This automatically forces all the policies to be the same. And there is this comment on, experience sharing for weakly homogeneous agents, but it's not, I don't think, they also don't have any learning curves for this. It's not exactly obvious why this works either, but this is again a thing that you could always do in any kind of task where, right, the agents are sort of randomized in some way, so they have to be interchangeable. You can do this too, but this is mostly the same as the independent DQN algorithm. I actually did try training this with the shared experience replay. Yeah, with IDQN. Again, like IDQN in general for these families of problems seems to be much slower and not perform as well as the policy-based learning. But here's an example of IDQN that learned this landmark task, relatively okay. The performance is still not great, right? Like this 0.6 indicates it's not, it's not actually succeeding every time. But this is with the experience replay, which should work for weakly homogeneous agents. And we can see it does appear to learn faster early on, because now the agents are able to learn from examples from all the other agents as well, even though they have distinct parameters. But it's possible I probably just need to train this longer, but it kind of leveled out here. If I allow this to train longer, it might eventually learn. But at least if training is cut off here after this many episodes, it does seem to be working somewhat, but not nearly as well as the policy. The policy learning, the results are like really, clearly obvious, especially right in the strongly homogeneous case, the advantage of parameter sharing when you actually have a problem that is suited to that. So that's all I wanted to say for this part of the chapter. So we basically covered everything related so far to, improving coordination between agents. And then next time, I have to decide. The next topics actually don't fit that well into what we've done so far in the chapter. There's sort of this diversion into Monte Carlo tree search and then population-based training. So I'm not sure exactly what we'll cover next time. This is a little more related to just like ordinary reinforcement learning. Yeah, but in any case, we are almost done with chapter 9. This will be the final topic that really is like a full-blown like multi-agent algorithm.